Okay, students, we are still at MOSFET topic. Okay, now MOSFET part 2, which is the AC analysis. So as you all know, AC analysis has two type of analysis. Okay, at mid frequency. Okay, at mid frequency, if you still remember mid frequency. Okay, this one we cover on the common source, common gate, and common drain. So the similarity of the analyzation for all these common. So common source is pretty similar to the common emitter. Common gate is similar to the common base, and common drain similar to the common collector. Okay, in this mid-frequency analysis, we draw the AC equivalent circuit by short circuit all the capacitor. Okay, all capacitor short circuit, and then you find all these parameter: the input output impedance, the voltage gain, the current gain. Okay, and then for the frequency response, okay, at low and high frequency, we will just focus on the common source. Okay, on the common source. All right. Okay, so this is how it looks like on the AC equivalent circuit. Okay, for the AC equivalent circuit, so you have the hybrid pi model as well. Okay, same like in BJT. Okay, so this is your MOSFET, NMOS. Okay, when current pointing in here, so this is NMOS. So the terminal gate, drain, and source. So this is the hybrid pi model. Instead, you have R pi and GM V pi. In MOSFET, you have VGS and GM VGS. Okay. In VJT, you have R naught. In MOSFET, you have RD. But most of the time, from now on in the test or final exam, usually we ignore the internal resistance R naught and RD. Okay, so for this one, this is that you need to know. Okay, in BJT, these are the parameters, small signal parameter. We call it as a small signal parameter. Okay, we find GM. So in MOSFET also, you need to find GM. So there will be two formula for GM. Okay, in BJT, only one formula, which is ICQ over VT. But in MOSFET, you have two formula. Okay, you can use either one, but make sure which value given. Okay, for example, given is the VGSQ and also the threshold voltage. Okay, you can find the GM by using this equation. Okay, if let's say VGSQ is not given, then you can use this formula to find your GM by using IDQ. So what is K? So K is a constant value. So K will be given. K is constant value. All right. In for the AC analysis, so we have common source. Okay, I know that common source you already know. Common source means, okay, when you have, okay, this is the example. Okay, this is the circuit of voltage divider. Okay, in the topic itself, you already know it is a common source. Let's say you don't know this is a common source, so let's go back. Okay, where is the input? The input is at the gate. Where is the output? Output is at the drain, and what's left is source. Therefore, this is common source. Okay, so this is how it looks like, the AC equivalent circuit. Okay. Okay, where you have VGS and GMVGS, and then from point to point, you draw the resistor. Okay. All right, and then we derive. Okay, so I have derived one by one. Case same like in BJT. So the derivation is pretty much straightforward. Okay, for this one, okay, for the Z in, okay, R1 parallel with R2, okay, Z out is equal to RD. Okay, and the AV V out over V in. Okay, V out is the voltage across the resistor here. So resistor here is RD. Okay, what is the current? So only current source is using over here, which is GM/VGS, but it is in opposite direction, so you have to put negative. Okay, if there is RL, then you have to parallel with RL. Okay, so we've tried this example, and then the second one is common drain. Okay, for the common drain, drain is to the ground. Okay, drain is to the ground. Okay, common drain is closely similar to the common collector in BJT. Okay, so this is how it looks like. Okay, uh, same like common collector. Okay, for the input part Z in, it is straightforward, R1 parallel with R2. But for the output, Z output impedance, same like common collector, where you have to apply V test and I test. Okay. I would like to say it here, okay, in the final exam, okay, or in the test for BJT, if let's say common collector is out, okay, you just say that Z out is parallel, Z out is equal to the RS parallel with Z test, okay. You don't have to, okay, this, why I show you this, okay, because for me, fundamental is important. Okay, I don't want my student to just memorize. Z test is 1 over GM. Out of nowhere, you don't know. Why 1 over GM? You don't know. Okay, that's why I show you here why we get 1 over GM. Okay, how we get 1 over GM is by injecting the V test. Okay, but then in the test, you can say that Z out is equal to the RS parallel with Z test. So Z test is equal to the 1 over GM. Unless the question said derive Z test, then this is what you should do. Okay, this is what you should do. Okay, if they didn't mention about derive the Z test, you can write the down Z test is equal to 1 over GM. Okay, and then Z out is equal to RS parallel with 1 over GM. Okay, that's how you do it. Okay, and then this is AV. I think same like in common collector. Okay, and then finally we have common gate. Okay, common gate. Okay, this one is similar to the common base. Okay, for the common gate, okay, gate is grounded. Okay, gate is grounded. So this is this circuit is quite straightforward lah. You can see that the input is source, the output is drain, so gate is left. So you draw the AC equivalent circuit. Okay, look at the current. So since this is NMOS, okay, NMOS, current pointing in is NMOS. So NMOS current drain is always from drain to the source, okay, going down like this. It is going down because drain is at the top, source is at the bottom. So meaning that current is from drain to the source. Okay, how you define your current source is to the left or to the right. Since this is NMOS, current is from drain to the source. That's why the current source here arrow to the left, because the current is from drain to the source. Okay, that's why to the left. Okay, look carefully whether it is NMOS or PMOS. So that defines the arrow of your current source, GM-BGS. Okay, same goes to the BJT, whether it is NPN or PNP. So it defines the current source arrow over here. Okay. All right. So this is the circuit. Okay. Same like this one. So Z in is quite straightforward because we have equal to RS. Okay. If you have RZ. If you have RG over here, it will be automatically ignored. Okay, why? Because IG is always approximately equal to 0. So when 0 multiplied with resistor, it will be short circuit. So straight to the ground. Okay, it's just here. Just left with GM VGS and negative VGS over here. Okay, like that. Okay, okay. So this one, okay, we haven't tried the example for this one yet. Okay, so let's take a look on this example. So this is a good example. Okay, ignore this one. Ignore this value G. Let me delete first. Okay, ignore this one because oops. Okay, ignore this one. Because this is for the common gate. In common gate, we don't have to find the frequency and everything. Okay, so all right. So in this question, okay, look at the question here. So this is the final year question. Okay, student, are you all there?
Yes.
All right, okay. So look carefully at the question, okay. So in this question, as you can see from here, okay, at first place, we don't know this is common gate, okay. So this is your MOSFET. So you know that this is the gate, okay. This is the real circuit, okay. So this is the real circuit, okay. For this example, it is quite straightforward. Okay, you know the input is source, the output is drain, and gate straight to the ground. Now, this is the real circuit. Okay, how you define whether this is common gate or not? Okay, like this. Okay, a gate, you have to put the sign of your gate. Okay, drain and source. Okay, since this is current pointing in, therefore this is an MOS, okay, and MOS, okay, and MOS. All right. So for this one, okay, where is the input? Okay, the input. So input is where the source is. So this is the input VS. Okay. And where is the output? The output is where the V out is. Okay. Usually the RL. So this is the output. Okay. What's left here? It is the gate. Okay. The gate left. So this is a common gate. Okay. Common gate. All right, now we want to draw the equivalent circuit. Okay, so this is very interesting. Okay, the circuit looks like very interesting. Okay, I will copy first. Wait, Okay. Okay, draw the mid-band AC frequency, draw the mid-AC equivalent circuit and determine GM, Z in and Z out, and determine the mid-band gain, okay, AV and also AI. Okay, okay, so this is, okay, doesn't matter. Okay, so this is the circuit. So first thing first, what you should do is, in order to draw the AC equivalent circuit, okay, at mid frequency, so all capacitor is short circuit. Okay, so this capacitor short circuit, this capacitor short circuit, and this capacitor also short circuit. Okay, so you have your gate, drain, and source. Okay, and all DC voltage also ground. Okay, grounded. So this one is grounded. All right. Okay, that's it. Okay, so let's draw the AC equivalent circuit. Okay, as you can see from here, this is NMOS, therefore current is going down from drain to the source. Okay, so look at the what we can say here. Look at the hybrid pi model over here. Okay, draw the hybrid pi model first. Okay, you have GMVGS and VGS over there. So let's draw the hybrid pi model. So you have the hybrid pi model GMVGS. We haven't discussed on this example yet, right?
Yes. Yes. Yes.
Okay, so this is the gate. Okay, gate is ground. Okay, so why gate is ground? So although you have RG over here, okay, but the capacitor is short, therefore it is shorted to the ground. Okay, if let's say you don't have capacitor over there, still RG is ground because IG is always approximately equal to the zero. Okay, All right. So what else do you have over here? So in BJT, you have VBE. If you still remember, from base to emitter, you have VBE. So that's replaced V pi in the AC equivalent circuit. But in MOSFET, you have VGS over here. VGS. Okay, as you can see, plus is at the gate. Okay, therefore here plus is at the gate, negative is at the source. Okay, that's why negative VGS. Okay, all right. Okay, so now gate is at the ground, that's why negative. Okay, now source. Okay, look at the source. Okay, now look at the source over here. Okay, source you have RS. Okay, you have RS. Okay, and then you have capacitor short circuit, and then you have R signal, and then you have V signal. Okay, okay, that's how you draw it. Okay, and then what's left is your drain. Okay, your drain over here. So this looks complicated, but when you draw from point to point, you definitely will get the answer. Okay, look at here at the first drain. Okay, so this is drain go to the RD2. Okay, where does this RD2 goes? Okay, so this RD2 will go to the okay, so these RD2, oh, different question. Okay, so this RD2, so this RD2 will go to this node, and then this node will go to the RD1, and then this RD1 will go to the RL. Okay, so you have here not to the ground. Okay, so you have RD2 over here, is it correct? Okay, and then RD1 to the ground. Okay, RD1 to the ground, and then from RD1 you have RL. Okay, RL. All right, you have RL. Okay, so this is your V out. Okay, so as you can see, you have from drain you have RD2, and then RD2 is split into RD1 and RL. So this is quite weird circuit. Okay, previously you didn't have this RD2 over here, but you have, and then you have RD1, and then you have RL. Okay, so for this one, okay, Z in is over here. So this is the Z in. Okay, before RS, so this is your Z in. Okay, and then your Z out is over here, which is before RD2. Okay, so this is your Z out. All right. Okay. Okay. All right. So this is for the AC equivalent circuit at mid-band frequency. Okay, at mid-band frequency. All right. So now you have here is the circuit over here. Okay, so in this case, okay, you have to, I need to copy first. Okay, and then we have to find the Z in, Z out, and everything here. So let me copy first. So the question asks you on the GM, Z in, Z out, determine the mid-band frequency. Okay, how you determine the GM? Oh, you need to, okay, so this is a continuation question. Okay, VGSQ is already given over here, but I have deleted it. Sorry about it. Okay, I have to delete this one. Okay. Yeah, VGSQ is given, therefore you can find the GM. Okay, VGSQ is 4.8 volt. Okay, 4.8 volt. Okay, so how do you find GM? Okay, so GM is equal to, okay, look at, since VGSQ is given, so you will be using the GM from the VGSQ, which is equal to the 2K VGSQ minus VTH. Okay, K is also given. So K is 0.4 milli. Okay, okay, 0. So 2 times 0.4 milli times VGS is 4.8 minus VTH is 3 volt. So here you will get like 1.44 millisiemens. Okay, so this is your GM. Okay, and now we want to find your Z in. Okay, Z in. Okay, for the Z in. Okay, for the Z in. All right, so Z in is equal to the RS. Okay, Z in is equal to the RS, but I think for this one, Z in is oh, in common base we have like 1 over GM, right? Can you go back to the did I derive somewhere here common base, common gate? Last time I didn't sempat derive 1 over GM, isn't it? Is it? No, only Z test. Is it? Sorry, I forgot. Oh, okay. So Z test for this one, common drain is 1 over GM. Oh, okay. Yeah. Okay. All right. So for this one, actually, okay. Oh, okay. I need to go back over here. Okay. So Z in is not equal to the approximately equal to the RS. Okay. So Z in you need to find same like common base. Okay. Common base you have the portion for 1 over r pi, if I'm not mistaken. Okay, so for this one also, we have another resistance. Do you still remember on the common base? Can you recall a bit on the common base? So for the common base, you have at the base resistor, if you still remember, 1 over r pi, if I'm not mistaken. Same goes to here. We need to find the ZS. So therefore, Z in is parallel with ZS. Okay, so I missed this one. Okay, I missed this one. But I will explain it here. Okay, so for the RS, okay, RS is parallel Z in. Sorry, not RS, for the ZS. Okay, so this is the ZS. So ZS is equal to the V in over I in. Okay, in this case, we need to know the I in. So let's just assume the I in over here is in this direction. Okay, so this is the direction of I in. So usually they will give the direction of I in. So that is the direction of I in. Okay, in here, this is the direction of I in. Okay, so for the V in is here over there. Okay, so V in is equal to what? Can someone give me V in? What is V in? Yes,
Negative VGS.
negative. Yes, negative VGS. Okay, what is I in? Okay, I in, the tips is actually by using KCL over here. So this is at this node. Okay, total current at node A here. Okay, total current at node A. So at that node, okay, I in, okay, I in is going in. Okay, and then you have also going in GMVGS. Okay, and also you have current here is IS. Okay, IS. Okay, IS. So current in is I in is equal to the, okay, let me just from here at node A, total current in is equal to the total current out. Okay, so current in over there is I in plus GM VGS equal to the I out, which is IS. Okay, therefore I in is equal to the negative GM VGS, okay, plus IS. So negative GM VGS, okay, IS is equal to what? What is IS? So let's use V is equal to the IR. Okay, so IS is equal to the V in over RS. Am I right? Okay, V in also, since we want to simplify the equation, okay, V in also is equal to the negative VGS over RS. Okay, negative VGS over RS. Therefore, this portion is equal to the negative VGS over RS. Okay, if you simplify this, you will get your I in over here. Okay, which is equal to the that value. Okay, now okay, let's just leave it like that. Okay, so ZS is equal to the V in over I in, which is equal to the, can I write it here? Okay, ZS equal to the V in over I in. Okay, it is also equal to the negative VGS. Okay, because we have found it here. Okay, V in equal to negative GM, negative VGS. And I in is equal to this portion. Okay, I in is equal to this portion. Okay, this is not IS, this is I in. Okay, this portion. Okay, it is over negative GM VGS minus VGS over RS. Okay, if you simplify this, you will get ZS is equal to the RS parallel with 1 over GM. Okay. Oh, yeah. Okay, this is actually straight away equal, not ZS. Okay, I'm sorry about this. This is actually Z in. Okay. Okay, so this is Z in. Okay, this is not ZS. So Z in is equal to the RS parallel 1 over GM. Okay, so this is how you get the Z in for common gate. Okay, for common gate. So not this one. Okay, so this is wrong. This one. Okay, so this is how you get for the common gate. Okay, so Z in is equal to the V in over I in. Okay, you have to find what is V in, what is I in. So V in is equal to the negative VGS over here. Okay, V in at this point, negative VGS. Okay, at node A, we use KCL at node A. I in equal to the I out. So total current over here is I in plus GM VGS equal to the IS. So IS is actually current across this RS, therefore negative VGS over RS. And you will get finally over here, sorry for the mistake here. So this is not ZS, so this is Z in. So this is also Z in. Okay, I in, right? So Z in, finally you will get RS parallel with 1 over GM. Okay, if they didn't ask you to derive, then you can straight away write Z in equal to the RS parallel with 1 over GM. But if let's say they ask you to derive, then you have to derive this thing. Okay, V in over I in, and what is V in, what is I in, and then you divide these two, you will get this simplification. Okay. Okay. All right, so let's go back to the question, to this question. Let's go back to this question. So in here, we know that Z int is equal to the okay, RS parallel with 1 over GM. Okay, in here, RS parallel with 1 over GM, RS, okay, RS is 1.2K, okay, 1.2K. Okay, parallel with 1 over 1.44 milli. So Z in over here, you will get 439.88 if I'm not mistaken. Okay, but this is a very old question. I have to check again. Can someone check again the answer? Hello?
A moment.
Yeah, I can understand.
All right, great. Okay, for the Z out, okay, Z out is we only take the for the Z out we only take the RD, the vertical resistor only, okay, which is what you see from here. So it is equal to the RD1, which is equal to the, where is RD1? RD1 or RD, yeah, RD1, which is 2.2K, okay, 2.2K ohm. Okay, all right. Okay, so for the V out, okay, for the V out, okay, what is the V out? Okay, so the question asks you to find draw equivalent circuit, check, and then determine GM, Z in and Z out, check, and then determine AV, V out over V in. Okay, let's see the V out over V in first. Okay, V out over V in first. So V out over V in. Can someone? So what is V out over here? V out is voltage across RD1 parallel with RL. Do you agree? Can someone give me what is V
Yes.
out?
Negative
TGM
GM
VGS.
Okay.
time RDL parallel RL.
Okay. RD1
1 parallel RL.
parallel RL. Okay. What is V in? Oh, I forgot to write here. This is the
Negative VGS.
in. Positive or negative?
Negative
VGS.
Negative VGS.
Yes, negative. Oh, sorry. What happened to me today? Okay, negative V in. Okay, so it is negative VGS. Okay, cancel out VGS. So you will get like negative GM RD1 parallel with RL. So this value,
Positive, madam.
yeah, positive. Thank you. Okay, so you will get the value, okay, apa, I will just write down because this is a very old calculation from myself, but that's okay. 2.2K, RL is 4.7K. Okay, in here you should get how much? 2.16. Okay, 2.16. Okay, student, hello?
Oh, okay, okay.
Okay, are you all okay with this?
Yes, yes.
Yes, ma'am.
Okay, okay, great. Okay, okay. So now, for the next one, I in, I out over I in. Okay, since that they ask you I out over I in, so look at the arrow. Okay, in let's just do it. Okay, although I know won't be asked about I out. Okay, doesn't matter. So the I out is over here, meaning that it is going down to the RL. Okay, going down to the RL. Okay, this is your I out. Okay, and then this one, sorry, I in. Okay, where is your I in? So I in is over here. Okay, I in is over there, which is equal across the R signal. Okay, let's just put the arrow. Why you have to put the arrow will be easier for you. Okay, so this is the arrow for I in. Okay, we know that. Okay, AI is I out over I in. Okay, all right. So I out over I in. So what is I out? Can someone give me what is I out? Just use the concept V equal to the IR. So I out is current across RL. As you can see in the circuit, current across RL. Current that flowing at RL resistor. Therefore, let's just put I out is equal to the V out over RL. Okay, I in. Okay, we already derived at here. I in is equal to the V in. Sorry. So this is your I in. Okay, this is your I in. You already have your Z in. Okay, this is your I in. Okay, we know that. Okay, in the equation just now, we know that V in is equal to the I in Z in. So I want to take I in over here is equal to the V in over Z in. Can I take this? Can. So this is equal to the V in over Z in. Okay, if you rearrange the equation, you will get here AV times Z in over RL. So that will be your current gain. Okay, so you have your AV over here, 2.16. Okay, 2.16. 2.16, and then Z in you already calculate here for 39.88 over RL is 4.7K, so you will get over here AI is equal to the 0.2. Okay, if you double check the question, you should get the same answer. Okay, the same answer. All right. Okay. So common gate is very, I think for me, easy. Okay. What make it difficult is the circuit here. Okay, the circuit here. It looks like complicated, upside down all the resistor. But then if you draw from point to point, first thing first is draw the GMVGS. And this one, the hybrid pi model, draw this first, and then you go from point to point, you will get actually the very simple AC analysis circuit like this. Okay. All right. So that's how you do it for the AC equivalent circuit. Okay. Okay. So that's it for the AC analysis circuit on the common gate. Okay. Why I have to show this because we need to look at the example in order to understand. Okay. All right. Now is on the low and high frequency. Okay, low and high frequency. Like I said, for the low and high frequency, only for the common source. Okay. If you still remember what in the BJT last time, if you want to find the frequency at low and high, okay, there will be two separate analysis. Okay, there will be two separate analysis. Okay, for example, so this is the, okay, ignore this symbol. Okay, should be the enhancement MOSFET. The signal is a dotted line here, dotted line. Okay, should be dotted line here, but this is straight line, so ignore this one. Okay, so we know that for low frequency, okay, for if you want to analyze the AC equivalent circuit at low frequency, which capacitor are you referring to? Okay, which capacitor are you referring to? Which capacitor for the low frequency? Student, hello?
Coupling and bypass.
Yes. Bypass? This one, okay? So for low frequency, only the what we call it, the capacitor that you can see, okay, the coupling capacitor. So this one, this capacitor, this capacitor, and this capacitor, okay? Coupling capacitor C1, coupling capacitor C2, and coupling capacitor CS. Okay, for the high frequency, you have to include all the internal capacitance. Okay, internal capacitance over here. Okay, so internal capacitance means junction capacitor where you cannot see, but you have to put it between the junction. Okay, between gate to the drain, between gate to the source, and between drain to the source. Okay, so this is the gate, this is the drain, this is the source. So you have to include all the capacitor junction, okay, as well as the the wiring out, that is the wiring output, okay, wiring output. All right, so let's take a look on the low frequency. Okay, so so these are all the capacitor. Okay, if you want to analyze the low frequency, what happened to the other capacitor? This one, the CGD, CGS, and CDS, that one is ignored. Okay, just put all the capacitor. Okay, for low frequency, actually you have to draw the AC equivalent circuit same like common source AC equivalent circuit. Okay, where you have the gate, the GM-VGS, and then you have RS, RD, RL, RG, and R signal. Okay, put all the coupling capacitor. Okay, this capacitor must be put. Okay, it is in between R signal and RG, so it is here. Okay, and then put capacitor this one, which is CS. Okay, this one. CS is in parallel with RS. Okay, so you put this capacitor over here, CS. Okay, so you will get this one, CS equal at this portion. And then you have another capacitor CC2, okay, which is in between RD and RL over here. Okay, just put all the capacitor. Okay, so how you analyze it? Okay, let's do it one by one. Okay, okay, meaning that sorry, I have to copy. Sekejap. Uh, okay, all right. Yes. Okay. Right. Okay, so you have three. So you need to find all the frequency at particular frequency at particular capacitor. Okay, so let's find the first one, FL due to CC1. Okay, due to CC1. Okay, which is this one, what you can see from here. Okay, so you need to in this case, okay, the voltage source is shorted. Okay, if you redraw again the circuit, okay, what you can see over here, CC1. CC1. Yes. Okay. So in here, the circuit will be like this. So this is the C1. Okay. And this is your RG, which is R1 parallel R2. And this is your R signal. And this is your CC1. Okay. Now, what is the R equivalent? Okay. In this case, FLC1 is equal to 1 over 2 pi. Okay, R equivalent CC1. Okay, what is the R equivalent over here? What is the R equivalent over here? R equivalent that you see from here.
R
R
SG parallel
signal
RG.
plus RG.
Parallel RG? No,
Series.
series. Okay,
Series.
yeah, series. You are seeing from top here. Okay, therefore R equivalent is equal to the R signal plus R G, okay, plus Rg. Okay, in this case, it is Rg, okay, plus Rg. So R equivalent equal to the R signal plus Rg, not parallel. Okay, you see from the top over here, it looks like in the series. It looks it's series. It is in series. Okay. Okay. All right. Okay. All right. Next is to find the FL. I want to use different color. Okay, FL due to C2 over here. FLC2. Okay, FLC2. If we draw the circuit, it will looks like this. So you have RD, CC2, and RL. So this is RD, this is RL. So what you see from here, so the FLC2, what is it? So FLC2 is equal to the 1 over 2 pi R equivalent CC2. Okay, what is R equivalent over here? What can you see from here for the R equivalent? What can you
Not
see from here?
plus RL.
Okay, so RD, this is D. Excuse for this one. Okay, RD plus RL. So it is in series. Okay. All right. So let's take a look on the number 3. Okay, FL due to CS. Okay, CS, which is over here. CS. Okay. All right. So for the FLCS, okay, so you actually have to find. Okay, what can you see? This is common like same like common emitter. Okay, same like common emitter. Okay, how do you find the RTH over there? So, so this one, so RTH. So actually, okay, actually, you need to find this one. It is actually how do you solve this in common emitter? Okay, to find Z out, how do you solve the Z out? It is same like common emitter. Common emitter and
Like
bypass,
test.
if you still remember.
Is it the Z test?
Yes, Z test. It is the Z test. Yes, it's the Z test. Okay. So, can you wait? I need to open the BJT file, but this very. Let me check. Where is it? Yeah, found it. Okay. All right. So it is Z test. I mean, common emitter for the unbypass actually. Okay, for the unbypass. Okay. So let me show you again. Okay, if you forgotten. Okay, so this is common emitter. Okay, common emitter unbypassed. Okay, where you have RE. Okay, so in here, oh, too far. Wait. Where is it? Okay, found it. Okay, found it. Okay, you have to find Z test. Okay, if you still remember. Okay, we detach our E, and then we find Z test, and then finally R out and everything. So this one we ignore. Like finally Z test is too large, and you will get the equal to RC. Okay, but then we have to inject V test and I test like this. Okay, like this. Okay, like this. Okay, V test and I test, and then you find the Z test. Okay, so we will apply the same method over here. But in MOSFET, it is much more simpler. Why much more simpler? Because they don't have resistor RPi over there. They just have the VGS. Okay, let's take a look on the circuit over here. Okay, so that's the idea, okay, on the V-test, okay. So what you should do is, okay, in this case, actually, you need to find the Z-test, okay, Z-test. Why? Because in this case, okay, your FL, okay, FLCS is equal to the 1 over 2 pi R equivalent CS. So R equivalent over here, it is actually equal to the RS parallel with Z test. Okay, parallel with Z test. So you need to find the Z test. How you find the Z test? You take out the RS, okay, and then you inject V test, if you still remember. So how you draw it? Okay, I think I need to show you how to derive it, but then later you can just take the value. Okay, so to find Z test, you need to detach, correct? Yeah, detach. Oh yeah, detach the RS and inject V test. Okay, this one. Okay, at this particular point, okay, you detach RS and you inject VS. Okay, you inject VS. V-test, sorry. So let's do it over here. So it is actually like this, okay? So I draw it again. So you have GM VGS and also V-test, okay? And also here, you already detach your RS, okay? So at this point, okay, you have where is your, yeah, the gate and source. Okay, therefore this is your gate and this is your source. So this is VGS. Okay, so Z test over here. Okay, so Z test is equal to the Z test is equal to the V test over I test. Okay, Z test equal to V test over I test. Okay, so I test is going down. So this is I test. Okay, same like you inject voltage previously. Oh my God. Okay. Okay. So what is V-test?
GM/VGS.
V-test only. Voltage. Okay.
VGS.
So,
V-test.
yeah. So V-test, you apply, correct?
VGS.
Someone, yes, VGS, you need to apply KVL over here. Okay, KVL over here. It is equal to the VGS. Okay, how about I test?
VGS. GM.
Yes, GM VGS. Okay, so in here you will get that Z test, it is actually equal to 1 over GM. Okay, 1 over GM. So go back to here. Therefore, finally, this one. Okay, so sorry. Okay, so this one, R equivalent is equal to the RS parallel with 1 over GM. Okay, so you don't have to derive it if they didn't ask you to derive, but you can straight away say that Z test is equal to the 1 over GM. Okay, therefore R equivalent is equal to the RS parallel with 1 over GM. Okay, so that's you do for the common source low frequency. Okay, common source low frequency. Okay, so let's take a look on the common source. So this is no derivation over here. Okay, but then you just took the derivation what I have shown you earlier. Okay. Okay. All right. So for the high frequency, let's go back over here. So high frequency, you should include all the internal capacitance. Okay. The wiring capacitance, CW in. Okay. CW out. Okay. The total wiring capacitance at the input and output. And also the junction capacitance. Okay. So CGD, CDS, and GS. Okay, so this one, the yellow highlighted one is for the high frequency. Okay, for high frequency. So for this one, it is quite long circuit. Okay, where you have to let me copy for a while. Okay, I need to copy this one. Okay, I need to copy this to this slide. Okay, so for the high frequency, you need to include this one, CGS, CW out, and CW in. Okay, what happened to all other capacitor? It will be short circuit. So other capacitor will be short circuited. Okay, so let's draw the AC equivalent circuit for high frequency. Okay, for the high frequency. Okay, so if you draw again, so you will get, so let's go from input to output. Okay, so you have GMVGS at the center. So this is your, okay, input is source. Okay, output is drain. Okay, and your bottom one is source. Sorry, this is input is gate. Okay, all right. So you have over here GM/VGS. Okay, your current source GM/VGS. Okay, let's go from node to node. Okay, from node to node. So you have okay, at the gate over here, you have RG. Okay, this is your gate. Okay, you have RG. Okay, you have RG. Okay, and then you also have your R signal. I want to draw a little bit back over here. So this is your RG. Okay, and then after that at the gate you have RG, and then you have R signal. Okay, R signal. Okay, and then you have here is your V hat, V signal. Okay, V signal. Okay, V signal. Okay, so that's it for the resistor. Okay, now you have to put your capacitor as well. Okay, at the input, you have your capacitor in here. What is the capacitor you have over here? At the input, okay, not to forget, you have CW in. Okay, sorry, CW in. Okay, CW in, total at the input. Okay, and then what you have from gate to source. Okay, you also have CGS. Okay, CGS. Okay, that's it. Okay, now let's go at the drain. Okay, at this drain, okay, you have RD. Okay, and then you also have RL. Okay, do not forget you have CW out. Okay, CW out, but at the drain and source you also have capacitor junction, which is CDS, so you have to put CDS over here. Okay, you have one more left with horizontal capacitor. What is the capacitor? Someone?
CGD.
Yes, CGD. Okay, this CGD. So you have this CGD. Okay, so how you solve this CGD? How did you solve this CGD? This CGD can be solved by using Miller theorem. Okay, I'm not going to show it again, but this is same like common emitter. Okay, by using Miller theorem. Okay, so this CGD, instead of it is in horizontal like this, we don't want this in horizontal. We want it in vertical, so it will be splitted into two. Okay, into two. Okay, it will be CM out and also CM in. Okay, last time in in the group, okay, your friend asked you different derivation in the textbook and also in the slide. Okay, please follow in the slide. Okay, please follow in the slide. I do not have time yet to double check in the textbook. Okay, at the moment, please remain same as in the slide. Okay, so at CGD will be splitted into two, CM in and CM out. Okay, then you have to redraw again. Okay, redraw again the equivalent circuit. Okay, so for now, the CGD no more over here. You're gonna have another one horizontal capacitor, which is here CM in. Okay, there is no more. And you're gonna have another one here, which is CM out over here. Where can I draw CM out? This is CM out. Yes, so that is the total capacitor and also total resistor. Okay, so in this case, so let me have one more. Let me copy kejap to the other slide. Okay. All right. So in here, you need to find the CM in and CM out. Okay. So for the CM in, okay, since this is CGD, therefore CM in is equal to the CGD. Okay. Times 1 minus AV. Is it the same one? Is it the same one like in the slide for the common emitter?
Yes, same.
All right. Okay. So let's stick with this one first, okay? Before I double check the textbook. Okay. All right. So what is the R signal? So what is the total R in? Okay. You need to find the total R input. So what is the total R input? So R input, you can short circuit this one. So this is your, can I use the R in? Okay, this is your R in, and this is your C in. Okay, this is your R out, and this is your C out. Okay, so in this case, CM in is equal to the CGD times 1 minus AV. So what is R in? What is R in? What can you see from here? If V signal short circuit, therefore R signal will be in parallel with, what is R in?
R signal parallel with RG.
Yes, R signal parallel with RG. Okay, and then F H, kita nak, I nak cari C in. Okay, so what will be the C in? Someone? Total C in, total capacitor over there?
CW in plus CGS plus CM in.
Yes, okay, CM in is this one. Okay, all right. So F high frequency referring to the input is equal to the 1 over 2 pi C in and R in. Okay, that's how you find the high frequency at the input. Okay, let's do at the output. So CM out in here, it is at junction gate to drain junction capacitor. Therefore, it is equal to the 1 AV minus 1 over AV. Is it right? Can you check with the common emitter? It's supposed to be same, right? Someone?
Yes, bro.
Yes, okay. So R out. What is R out? Total R out?
RD parallel RL.
Yes, RD parallel with RL. What is C out?
CMO plus CDS plus CWO.
Yes, CW out. Okay, so FH due to the output is equal to the 1 over 2 pi C out R out. Okay, so this is the FH out. Okay, high frequency due to the output and due to the input. Right. So this is done for the high frequency. Okay, we have actually derive both for the low frequency and high frequency at common source. Okay, common source only. Okay. All right. So this is derivation. Okay. So we have done everything on the for all common. Okay, for all common, if you look at it, okay, you have derived for all common, and also at mid-band frequency and also at high frequency. Okay, I already upload the question, the tutorial question on the e-learning. Okay, I combine all the DC and AC analysis. Okay, can you try it and we will discuss on the next class. But today I would like to discuss, since we don't have example for the high frequency and low frequency in the slide, I would like to try this question with all of you. Now, okay, can you refer to your to your slide? Sorry, can you refer to the e-learning? I already upload. Okay, so since we don't have the example, okay, in the slide, I will take this example. Okay. All right. sorry, I forgot. We didn't have uh, take 5. Okay, let's take 5. Sorry, I forgot. Okay, so let's take 5 first, okay, before we try the tutorial question. Okay, so you at the moment you can download the tutorial question. Okay. Hello? Can you all hear me? Hello? Hello?
Yes.
All right, okay. Okay, so someone asked me, do we need to draw the AC equivalent circuit for high frequency for twice before and after Miller theorem? No need. Just draw one after the Miller theorem. Okay, just draw once only. Okay, right. Can you see the tutorial question that I'm sharing now? Okay, so this is tutorial question for the MOSFET. I combined both DC and AC analysis. So I actually combined the interesting question from the past year as well. As you can see from here, let's just go through over here. Okay, let's just go through over here. I just want all of you to define. Okay, so this is simple. So what common is this circuit? Okay, can you all see? Question number 10. So what common is this? Okay. What common is this?
Common drain.
Yep, it is common drain. Okay, so you have the gate over here. Okay, and then you have drain, and then you have source. Okay, as you can see, the drain is to the ground. Okay, therefore it is a common drain. Or else you can look at like this, where the input is at the gate. Okay, this is the input, and this is the output. Okay, at the source. Okay, therefore what's left? Drain. This is common drain. Okay, so let's take a look on this circuit. Okay, this is very upside down circuit. Please expect your test 2 on the BJT also this kind of complicated or upside down circuit. But then if you define one by one, where is the input and where is the output, and you determine what type of common, then there will be no wrong. Okay, after that you can draw your AC equivalent circuit from point to point. Okay, how about this one? Okay, how about this one? Okay, so this is it the same like in the example? No, not the same. Okay, so what common is this? Can someone give me the answer? So this is gate, drain, and source.
Common gate.
Common gate. Okay, common gate. So look at the input. Okay, where is the input? The V signal, of course. So this is the input. Okay, at the source. Okay, at the source. And where is the output? So output is belong to the RL. So output is connected to the drain. Okay, therefore what's left is gate. This is common gate. Okay, quite similar to what you have done actually. If you can see in the example of common gate just now, it is quite similar. Okay, you see the circuit cannot be hard enough, but it is just the lecture tweak here and there. Okay, so the gate over there you have RG1, and then RG2 is parallel with capacitor. Therefore, RG2 is short circuit and it is common gate. Okay. All right. Another thing is, if you notice, so this is a very good example. So you have two sources over here. Okay, you have VD plus VD, and also you have minus VD. Okay, what happened to these two sources in AC equivalent circuit? So both will be
Ground.
Grounded.
Grounded.
grounded. Okay, grounded. Okay, please in the test 2 later, look carefully how many voltage are given, and in for the AC equivalent it will be grounded. Okay, it will be grounded. Okay, so this is very interesting question. Okay, all right, but today I don't want to discuss this. Okay, I just want you to guess what common is that. Okay, I want to discuss this one. Okay, this example. Okay, but before that, I think you can try later on your own. So what common of this circuit?
Common source.
Yes, common source. Okay, so this is the input. Okay, at the gate. Okay, this is drain. Okay, this is the output. Okay, and this is the source. Okay, left is source. Therefore, this is common source. Okay, that's how you define it. Okay, And yeah, one more thing over here. This is also common source. Okay, you can try later. Okay. All right, now let's us try this example. Okay, so this is from the past test 2020-2021 final exam. Okay, given blah 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 everything here given. Okay, given everything. Okay, you need to draw the AC equivalent circuit at mid-band frequency, and you need to find the dominant low cutoff frequency. Okay, low cutoff frequency. So I was telling you this. What is this? Okay. First thing you have to find the F low frequency. Okay, so this one, okay, what common is this? Although you don't have V signal, but you have V in over there. Therefore,
Source.
yes, common source. So this is the input. So this is the output. Okay, this is drain. Output at the drain, input at the gate, and this is source. Therefore, this is common source. Okay. All right. So draw the AC equivalent circuit. Okay. So let's draw the AC equivalent circuit. Let me kecilkan. Oh. All right, just like that. Okay, so draw the AC equivalent circuit. You have to, what you have to do, okay, draw AC equivalent circuit. Okay, in here, you need to draw AC equivalent circuit. This is common source. Okay, common source. All capacitor. Okay, short circuit. Okay, and also DC voltage. Grounded. Okay, grounded. So this is grounded. So this is short circuit. All right. So let's draw the AC equivalent circuit. So AC equivalent circuit, first thing you have to draw the hybrid pi model. Okay. This is since this is unbypassed, okay, because we don't have capacitor at CS over here. If you can see, we don't have capacitor over here, where you have to include also your RS in the circuit. Okay, so we know that this is the drain. Okay, I keep drawing it this again and again. So this is the source. Okay, may I know the GM VGS is going down or going up, the arrow? So this is what type of MOSFET is this? Is this NMOS or PMOS?
NMOS.
NMOS. Okay, NMOS. Therefore, ID is going down from drain to the source. Okay, therefore here ID is going down from drain to the source. Okay, and at source, okay, we have RS. Okay, we have RS. Okay, this is your RS. Okay, and don't forget you have from here, this is your VGS. So this is your hybrid pi model. Okay, done. Okay, let's draw at the input. What do you have at the input? Okay, at the input, which is your gate, you have your R1 to the ground, and then R2 also to the ground. Therefore, at the input, you have R1 parallel with R2 to the ground. Okay, so that is your input. Okay, parallel R2 to the ground. Okay, and then what else you have? Nothing else. So you just have V in. Okay, V in. V in. All right. Okay. So at the drain, okay, at the drain, at source done, at drain, what do you have? So at drain over here, you have RD to the ground, and then you also have short circuit C2, and then you have RL to the ground. Okay. Therefore, at drain, you have RD, okay, and also you have RL. Okay. This is plus minus V out. Okay, so you have RD and RL. So where does the arrow of the Z in and the Z out? So just put it here. So this is your Z in and this is your Z out. Okay, so that's it. Okay, so this is for the part 1. Draw and label the small signal hybrid pi AC equivalent circuit at mid-band frequency. Okay, why they ask you to draw this? Because it will be easier for you to find the frequency later on. Okay, so in here, oh. All right, so the second part, okay, find the low frequency. So they ask you to find the low frequency, okay. So how many capacitor do you have in the circuit? So you have 2 capacitor, okay, C1 and C2, okay. Therefore, so number 2, I need to, oh, no. Okay, so this will be your number 2. Okay. Mm -mm. Okay, so this is your number 2. Okay, in here. All right, so what you should do is, okay, the capacitor, where is the capacitor? Capacitor C1 is at the input and C2 at the output. So this is your capacitor. Okay, so C1 is before RL and C2 is after, sorry, in between RD and RL. Okay, so this is your, okay, let me draw again. Where is, and okay, so this is your C1 and this is your C2. Okay, right? So now we want to find the FLC1 and also FLC2. Okay, FLC1 and also FLC2. All right, so it is actually from here, okay, what you see. So FL, okay, due to the C1 is 1 over 2 pi Z in and C1. Okay, so what is Z in? What is Z in? So due to the C1, okay, if I redraw again over here, so you should get like something like this. So this is your one. Okay, so this is C1 and this is R1 parallel with R2. Okay, and this is the Z in. So therefore, FL due to the C1 is 1 over 2 pi Z in C1. So what is Z in? What is Z in? Student?
R1 parallel R2.
R1 parallel R2.
Yes, R1 parallel with R2. Okay, you don't have R signal, therefore you don't have to plus with R signal. Just Z in. Okay, so R1 parallel with R2 is equal to the, what is the value? Oh, Z in given. Look at the question. So, oh, this question is interesting. Oh, I know why, because it is a continuous question. Okay, so IDQ given, VGSQ given, Z in also given. So Z in is 372K. Okay, Z in is given, which is 372K ohm. Therefore, FLC1 is equal to the 1 over 2 pi 372K. C1, what is C1? Is C1 also given? Is C1 given? The question? Yes, 0.1 micro. Yes, 0.1 micro. So here FLC1 is equal to the 4.27 hertz. Okay, 4.27 hertz. All right. So now FLC2, Okay, FLC2. Now let's find for the FLC2. Okay, FLC2. So let's redraw again the circuit. So FLC2 is equal to this one. Okay, this is C2. This is RL. Okay, so this is Z out. Okay, Z out. Let's just put here Z out. All right, so this is interesting. Okay, so how do you find? So in here, therefore, FLC2 is actually equal to the 1 over 2 pi Z out plus RL times C2. Okay. My question is, what is Z out? Okay, if you refer back to the common emitter unbypassed, okay, how do you find Z out? Still remember? Do you still remember how you find Z out? By using what?
Z-test.
Yes, by using Z test. Okay, so you need to find here. What I can say, you need to find here. Okay, the Z test. Okay, Z test. Okay, you need to look at the derivation in the common emitter. Okay, you should be able to derive it. Therefore, Z out is actually equal RD parallel with Z test. Okay, RD parallel with Z test. Okay, so Z out is actually equal to the RD. Oh, sorry, RD parallel with Z test. Okay, so don't want to derive it. So, but it is actually equal to the V test over I test. Okay, V test over I test. All right. Okay, and then you apply VTS and so on. So you should get it's actually the derivation in here. So if you I just give you some hint, okay, how to find the V test and I test. Okay, I just give you some hint. Okay, if you look at the slide just now, you find Z test is V in over Vn. So actually what you can do is you can inject voltage at the drain to source. Okay, you can inject voltage at the drain to source, and then you find Z test. Okay, this is how you can do. Okay, I just give you the idea how to find Z test. Okay, Z test. So you inject over here. Okay, so you have here drain. Okay, so this is your V test, I test. Okay, so this is your V test, I test plus. Okay, and then you have over here GM VGS. Okay, this is RS. Okay, and then over here you have plus minus VGS. Okay, this is your gate. Okay, so how do you find your Z test? Z test is over here. So this is your V test. Okay, so Z test, finally you will get, so Z test is equal. So okay, so in this question looks like you have to derive. Okay, or if you don't want to derive, if you remember, then that's okay. So finally you have to find this V test over I test. Okay, so V test is equal to the VGS plus GM VGS RS. Okay, I have derived so many